Hi, and welcome to Rosie STEM. Today we're going to be talking about a topic that could span an entire college course, linear regression. In today's video, we're going to be covering simple linear regression specifically, and we're going to give an introduction to the concept of a regression. In future videos, we can cover model diagnostics and more complicated analyses, so let me know what you'd like to see in the comments down below. Simple linear regression refers to a regression with just one feature variable x and one response variable y. So let's start with a question. Suppose I'm trying to sell my house and I'm not sure what price to put it on the market for. I do some searching and find other houses in my area that have sold recently, and I take note of their price and their size. And I plotted all of my data here in orange. My house is right about here at this green mark, and there are actually no other houses in my neighborhood that were the same size as my house, so I still don't know what price to sell my house for. Is there a way that I can still use this data to help me decide? Well, the data follows a pattern. As the size of the house increases, so does the price. And this pattern seems to be linear, meaning that the amount the price increases for a change in size stays the same as size increases. In other words, the slope is constant. I could draw a line through these points and it would provide a pretty good estimate of the pattern or trend here. Then I could use that line to give me an idea of how much houses of each size sell for on average. Once I have this line, I can use it to find a good selling price for my house. But there are actually a lot of lines that I could draw through this set of points. In fact, there are an infinite number of lines that I could draw, and each line would give me a different estimate for the average price of my house. So how do I know which line is best and would give me the best possible estimate? Well, the best fitting line should be close to the center of the cloud of points, but I don't really have a way of measuring this. Here, I've drawn a few more orange points and a blue line through those points. The way we measure how well a line fits points is to calculate something called a residual. A residual is the vertical distance between a point and a line. So we calculate it by looking at the y value of the point, y, minus the y value of the line, which we call y hat. The hat indicates that this value is an estimate coming from our line. In this diagram, each green line is a residual. Each orange point has an associated residual. The line that best fits these points will be closest to the center and will then be the one with the smallest residuals. To compare different lines, I can add up all the residuals and pick the line with the smallest sum of residuals. But in reality, we need to do more than just add the residuals together. For example, consider these orange points. They lie exactly on this blue line. This line would be the best fitting line to these points. All of the residuals are 0, so the sum of residuals is 0. It's clearly a better fit than, say, this line. Let's calculate the residuals for this line. From left to right, the residuals are -3, -1, 1, and 3. These actually also add to 0. So if we just add the residuals up, both of these lines look equally as good, but we know they're not equally good fits to the points. So how do we get around this? Instead of just summing the residuals, we can square them first so that the negative and positive residuals don't cancel out. Now we still get a total of 0 for the first line, but for the second line, we end up getting 20, which reflects that that line is actually a worse fit to the points. We call this method the sum of squares method, and this calculation is called the sum of squared errors, which we abbreviate as SSE. Or sometimes we call it the residual sum of squares, which we abbreviate RSS. Usually we also divide this by the number of points, and then we call it the mean squared error, or MSE. These are all versions of the same measurement, and you might hear all of these terms used almost interchangeably. But this isn't the only way that we can measure how well a line fits data points. There are actually a lot of measurements that we could come up with. For example, we could also take the absolute value before we add the residuals instead of squaring. So this is called the sum of absolute errors. Or if we divide by the number of points, like we did before, it's called the mean absolute error, or MAE. We can think of these as measurements of how well a line fits the data, where low values are considered better fits and higher values have more error. Another name for a measure like this is a loss function. This term is commonly used in machine learning, and to find the best fitting line or the best fitting model, we want to find the model that gives us the smallest error or the smallest loss. So we have to find the line that minimizes our loss. So how do we define our loss as a function that we can minimize? Well, first let's write the equations for our residuals and sum of squared errors. For every point I, we sum the squared difference between the true y value and the predicted y value from the line. So our yi hat here actually comes from our line, and we know from algebra that lines have the equation slope times x plus intercept, or sometimes we use the term mx plus b. So let's plug that in for our y hat. If we want to minimize our sum of squared errors, we need to find the values of our slope and our intercept, in this case m and b, that would make this equation as small as possible. We have fixed yi's and fixed xi's, so the only thing here that we can change is our m and our b, our parameters for our line. For those of you who have taken calculus, we can do this by taking the derivative of our loss function and setting it equal to 0, then solving for m and b. But for the purposes of this video, we're not going to solve for these ourselves. Let me know in the comments if that's something you'd like to see in another video, but for now, I'm just going to give you the equations. So these are the values of the slope and the intercept that minimize this squared error. So they're the estimates of our best fit line. And since we are usually estimating based on a sample, not the entire population of possible house sizes and prices, we give them a hat as well. We call them M hat and B hat since they're estimates, they're statistics, not parameters. The x and y with the line over the top we call x bar and y bar, and they actually represent the mean of our x values and y values respectively. So m hat is equal to the sum across all of our points of the x value minus the average x value times the y value minus the average y value. Then we divide that by the sum across all points of each x value minus the average x squared. That gives us our estimate of the slope. We have to calculate that first because then we use it to calculate the estimate of our intercept, our b hat, which is equal to our average y across all points minus our estimated slope times our average x across all points. Once we've calculated this m hat and b hat, we have the equation for a line, and we call that line the least squares line because it gives us the smallest or least squared error. We cannot necessarily do this same method of minimizing errors with our absolute squared error because it doesn't have the same nice properties that allow us to take the derivative. If you've taken calculus, you know that when you take the absolute value of something, like the absolute value of x, that function is not differentiable. So we can't get these nice closed form solutions, and by closed form I mean nice equations that we can just plug things in to calculate our slope and intercept. But that doesn't mean that we can't use our mean absolute error as a measure of error to find a best fit line. There are computational optimization methods that you can use to find the best possible lines according to our mean absolute error. Now that you understand the motivation behind simple linear regression, you have the basis to start building regression lines of your own. In the next video, we'll go through some examples of how to find the best fitting lines using mathematical methods with mean squared error, as well as computational methods with mean absolute error, and we'll also try out some built-in functions in Python using the modules scikit-learn and stats models. But until then, thank you all for watching. I hope you learned something new about loss functions or simple linear regression. And if you did, I'd appreciate if you give this video a like and comment to let me know what you learned. Please also let me know what other videos you'd like to see down below. I want to make sure I'm making content that's useful for you. And I'll see you in the next video where we'll be working through some examples. Bye.